Welcome to Exam List. So in our last lecture, we're discussing about kinetic energy, rotational kinetic energy. So what are the things we have discussed? So if you have a string, massless string, and if you have a ball attached here, and say it is of mass m, and the ball is rotating with a velocity v. Okay. So by rotation, I mean it is literally making a circular path. Then what is the kinetic energy? The kinetic energy was said to be half mv square. Agreed? Now, as I said earlier, let us do one thing. Say consider this is of mass m and this is velocity v1. Okay. Now consider another ball of mass m placed here. Then what is the total kinetic energy system? Then the new kinetic energy will be the kinetic energy of first ball and kinetic energy of second ball. So second ball has a velocity v2 square. I mean the second ball is rotating with a velocity v2. Now what you do is, now you place a third ball. So when you place a third ball, then this system will have a kinetic energy half m v3 square. In this manner, you go on placing one after another. Say there are n number of balls. How many balls? N number of balls on the string. Okay. And now if I ask you what is the kinetic energy, you know that all the ball will have different linear velocity. The ball which are far away from the center will have greater velocity, that v1 will be greater, and the ball which are very near, say the nth ball which is very near to the center, will have a very low velocity, and the total kinetic energy will be addition of the individual linear kinetic energy of all the balls. Agreed? Now to calculate the kinetic energy of n ball system, if I just write every velocity as a multiplication of the corresponding r square and omega, since we know that omega is same for all the n balls, so I can write omega square here. So I'll be left with only terms like m r1 square for the first ball, then m r2 square for the second ball, and so on. It means when you have an n ball system, you are actually adding individual moment of inertia. Isn't so? Look at this. What are you doing here? You are actually adding all the momenta. Similarly, if the n number of ball goes to infinity, then what do you get? You get an object that looks like a rod. Okay, if the number of ball goes to infinity, then you'll actually get an object that looks like a rod, and this rod is fixed at a particular point O, and now the rod is rotating. Agreed? So what is the higher version of addition? The higher version of addition is integration. So this is what? This is nothing but summation m r I square. I mean all the I going from 1 to n is getting added. This is when you have discreteness. But when you have continuity, then you need to use integration. This rod is a continuous mass object. You have to use integration. So now the thing is how to calculate the moment of inertia of a rod. Okay, let us see. Now imagine a small, very small part of the rod, and let this part of the rod be dx. Now imagine that the complete rod has a mass m and a length l. Then what is mass per unit length? That is lambda, that is m divided by l. Now I have considered a very small part of the rod, that is dx, and let this dx is at a distance x from the center. Then can you tell me what is the moment of inertia of this small dx part? Now what is the mass of dx? So mass of dx will be lambda into dx. This is the mass, and this mass is present where? This mass is present at x, and you need to do what? You need to square the presence value of x. I mean, wherever the mass is present, you take that position and square it. This is what you do. Then what is the total angular momentum? Obviously total angular momentum will be lambda x square dx, and obviously you will integrate it from where to where? From 0 to L. This integration is very simple. Lambda goes out, it's constant, it's mass per unit length, and inside you'll get x cube divided by 3. But from where to where? From 0 to L. Now what is lambda? Lambda is m by L. And what is this? The remaining term is 1 by 3 L cube. So what is the moment of inertia of rod? It is 1 by 3 m L cube. Amazing, right? So it's a very simple calculation, just simple use of integration, and we found that the moment of inertia of a rod is half ml3 square. Now if I tell you that this rod is rotating at a velocity, at an angular velocity omega, then what is the kinetic energy? You will say, hey look, kinetic energy is very simple. All you have to do is half and moment of inertia into omega square. And since we already know what moment of inertia is, so we have to do half. The moment of inertia is 1 by 3 ml cube. Okay, and then the angular velocity square, that omega square. That's it. This is the total kinetic energy of a rod rotating at a constant angular velocity omega. So in this way, you can use integration to calculate the moment of inertia of continuous object. Now why are we calculating the moment of inertia? Because total moment of inertia multiplied with omega square directly gives us kinetic energy. We don't have to individually calculate the kinetic energy of every term. Agreed? So this is the magic of moment of inertia. You add all the moment of inertia, you get the total moment of inertia, and square it with the angular moment, angular velocity square, you get the total kinetic energy. So it helps us reduce a long calculation. It helps us reduce a long calculation. If you would have done a long calculation, what you have done? You would have added the kinetic energy of all the small parts. I mean, you would have taken so many dx here and here and here. All of these dx will have a different velocity. Okay, so that would have been a hectic work. So instead of that, we just calculated the moment of inertia. Once the total moment of inertia is calculated, you can easily find the angular momentum. You can easily find the kinetic energy, not angular momentum. Agreed? So I hope you understood rotational motion and what are the terms. So what did you learn in rotation? You learned about tau, you learned about angular momentum, you learned about angular acceleration, you also know what omega is. Now you know what is kinetic energy, you know the analog term, that is moment of inertia, and you know how to calculate the moment of inertia of continuous objects. Agreed? So I guess you understood all these things. So we'll continue more with our basic classical mechanics in the next lecture.